Hi everyone, my name is Silvan Fischbacher. I'm a PhD student at ETH Zurich, and today I will be talking about GalSBI, our galaxy population model that can be used to forward model galaxy surveys. I would like to start with a very broad overview of how we get from observations to cosmological constraints, and this mainly in the context of a photometric survey. So we start with an observation, and this consists typically of many single exposures. They have background noise, they have a PSF, and we stack these individual exposures together and then get the astronomical image that we are using for our analysis. From this image, we want to obtain a catalog, so we have to perform some kind of source extraction on this image, and we further have to do some quality cuts that the sources that we actually have in this catalogs are only the one that we actually trust in the quality. So we have to perform some selections, have to remove stars, remove objects where we are not very confident in our photometry and so on. If we think of a cosmic shear survey, we further have to measure the shape of these objects. So we have to do a shape measurement for all objects and then add the corresponding shape parameters also to this catalog. From this catalog, we cannot move directly to the cosmological constraints or neither to the summary statistic, because we need some kind of photometric redshift estimation to do that. So we have to estimate the photometric redshift distribution of the object in this catalog. And after we have done that together with the catalog, we can compress this in some kind of summary statistics. So for example, a 2-point correlation function. And from there, we can do our classical Bayesian in inference to obtain our cosmological constraints. In all of these steps, there are a lot of challenges. I would like to highlight two of them. One is the photometric redshift estimation. And this is already for stage 3 surveys, one of the main systematics. If you look at the results from the HSC year 3 cosmic shear sample, here we see the third and the fourth redshift bin. We see two things. First of all, we see that the spectroscopic redshift that can be used for calibrating goes only up to redshift of about 1, which means that the very high redshift bins are not very well captured by this calibration data. We further see in the solid lines then their fiducial photometric redshift distribution. And then in the dashed line, we see how much this distribution was shifted after introducing uninformative priors in the Bayesian analysis. And you see that this shift from the solid to the dashed line is actually quite significant. So this means that we're already now quite limited by our ability to obtain a good photometric redshift distribution. Either we get biases if we're sticking to our fiducial redshift estimation, or if in that case we use very uninformative priors, this can lead to an increased uncertainty on cosmological parameters. And both of these scenarios we would, of course, like to avoid now that we are moving on to stage 4 surveys. Another challenge that will become even more challenging when we go to deeper stage 4 surveys is source blending. So here you see 4 times the same patch of the sky with an increasing depth. And the deeper the data is, the higher is the chance of source confusion, so that you have 2 types of objects very close to each other, and you're maybe not able to distinguish them anymore. And this does impact your detection probability, but it can also impact the accuracy of your shear measurements when you have objects that are very close by or even overlapping. One option or one possibility to tackle these problems is forward modeling. And one forward modeling framework that I would like to advertise here is GalSBI+. This is a galaxy population model based on stellar population synthesis. We put that on the archive just a few weeks ago. And if you're interested in this model, I would refer you to Luca Tortorelli's talk. He will give more details about GalSBI+. I will be talking about the phenomenological counterpart of GalSBI+, and how we built this model and also how we constrain this. GalSBI is a parametric galaxy population model. So this means we can decide on a certain set of parameters. And after we have decided on that, we are able to sample galaxies from that. For example, we can say we want to have a galaxy catalog corresponding to a certain patch of the sky. And we can generate such an intrinsic catalog that has intrinsic magnitude, sizes, light profiles, and so on. This catalog can then be used to render an astronomical image. And here, of course, we have to somehow match the background and the PSF and other image systematics of the real data. And therefore, we have to estimate these background level and PSF levels from this real data. The rendering is then done with the ultra-fast image generator that we also have developed for this. Then we have the simulated image and the real image, and we perform the source extraction and all the further selections, and we do that consistently, so the same way on the image of the real data as well as on the simulated one. So now we get two catalogs, one a catalog of simulated objects and one of the catalog of the real image, where we have for both the measured sizes, their measured magnitudes, measured ellipticities, and so on. In the beginning, we don't know which parameters we should choose for our galaxy population model. So we actually want to constrain the parameters of our model. And we do this with a simulation-based inference. And in our very specific framework, we use an iterative implementation of ABC, so approximate Bayesian computation, where we compare the measured catalog of the simulations with the measured catalog of the data. And in this comparison, constrain the parameters of our parametric galaxy population model. Because this inference is quite resource intensive, we also developed an emulator that basically learns the transfer function from the intrinsic catalog to the measured output catalog. After we're done with this inference, we get the constraints on the model parameters. So we have a posterior distribution, and we can then use this posterior distribution on these model parameters to generate again, an intrinsic catalog for a specific sky area. And now this intrinsic catalog is also realistic in its galaxy population. So this means if you're now generating this image, it has a realistic background and PSF level, which we estimated from the data, and it has a realistic galaxy population because we use our constraint model. And therefore, we can produce very realistic images. And these can then be used to all kinds of image-related calibrations. So for example, we can calibrate our shape measurement with that. But we can go further. We can now, again, do the source extraction and all the selections on the image the same way as we do it on the data. And now, since the galaxy population model is constrained by the data, the catalog that we get from the simulated image and the catalog that we get from the real data should be statistically consistent. This means we can basically forward model all types of selection effects that could happen in our selection process. And because in the simulation, we of course know the redshift of each object, we also get basically for free an estimate for the redshift distribution in the real data. In this talk, I would like to focus on this part of the pipeline, so on the galaxy population model and how we obtain an intrinsic catalog. In GalSBI, we define the population by basically a split in two populations, one red, more passive galaxies, and the other one consisting of blue, more star-forming galaxies. The backbone of the model are then luminosity functions. So this is illustrated here on the right. So the luminosity function tells you how many galaxies at what brightness exist. You also see illustrated here the different parameters that we use to parameterize the luminosity function. If you would like to get a bit more intuitive understanding of how this parameter affect the luminosity function, then you can use the link here, or also the QR code here. There we have an interactive version of this plot, where you not only see how the luminosity function changes the shape, but also directly how it impacts an astronomical image. So if you have suddenly more objects due to the luminosity function, you will see it in the astronomical image, how more and more galaxies populate the image. The luminosity function just gives us the redshift and the absolute magnitudes of the object. If we want to do image simulation, we of course are interested in the apparent magnitude. And for this, we need to assign a spectrum to these galaxies, which we do by using these k-correct templates. Basically, each galaxy is a linear combination of these different templates. This gives a spectrum. This spectrum can then be integrated over the filter throughput where we want to do our simulation, and we get the apparent magnitudes. Then we have a size model that depends on the luminosity and also evolves with redshift to assign physical and angular sizes to each object, and we also have some flexible parameterizations for the light profiles and for the shape, such that we then can assign a Sersic index and also the ellipticity to each of these galaxies. In total, this gives us 53 parameters that we constrain in this model using SBI. I would now like to make a short detour and talk about positions. So up to now, what we did is we randomly sampled positions from a uniform distribution. This is, of course, very simplified because we know that there is clustering in real life, and we did not include clustering in our simulations. And now we're working on actually including clustering effects using a subhalo abundance matching approach. This is all heavily based on the work by Pascal Berner in her PhD. The general idea is as follows. We start with a full sky dark matter only simulation. In our case, this is done with Pinocchio. And Pinocchio gives us a halo catalog and the corresponding merger trees. From the halo catalog and the merger tree, we are assigning subhalos to this catalog, also following the first paper by Pascal Berner. And then we classify each of the halos and subhalos as hosts for red and blue galaxies. And the model for this depends on two parameters, the mass limit for the central halos and the quenching time for the subhalos. So basically the very massive central halos are red and the less massive halos are blue. And for the subhalos, we basically have subhalos that just when they merge into the main halo, they're blue, and then after a certain quenching time, they quench and turn into red galaxies. This gives us now a catalog of halos that host blue galaxies and a catalog of halos that host red galaxies. And we just have to basically now assign the GalSBI galaxies to these halos such that they get their position. Up to now, the way we had to do this was with like the standard subhalo abundance matching approach, which means we have this very large halo mass catalog, including the positions that we get from the dark matter only simulation, so in our case Pinocchio. And then we had to basically sample galaxies with their absolute magnitudes from GalSBI in the same survey area. And this typically had to be quite had to cover quite large volumes, since we did not want to be dominated by cosmic. From there, we had these two very large catalogs, and then we needed to sort these two catalogs. And after sorting, we could then obtain the matching relation. So we assigned the heaviest halo in the catalog to the brightest galaxies, and then continue down. And this matching relation could then be applied to the smaller halo catalog that is, for example, in a very specific part of the sky that we want to use in our image simulation, and then assign the absolute magnitudes there. This is not very efficient because we always need to generate this very large catalog, and also the sorting of this very large catalog is quite resource intensive. This is why we developed the SHAM-OT framework, where we can do this much more efficiently with optimal transport. The basic idea behind this is that instead of generating large catalogs, we're working on a histogram representation directly. So we get a histogram, so the halo mass function that we estimate from the simulation, and then we can use the analytical luminosity function from GalSBI and use optimal transport to directly match these two. So we get this matching relation. Instead of generating large catalogs and sorting them, we basically get this by matching these two histograms in like fractions of seconds. And this matching relation that we obtain here can then be applied to the very small catalog that we need for the part of the sky that we want to simulate in image simulation. So we can basically do all of this without any sampling or sorting. And overall, this gives us a speed up of about 2 orders of magnitude. So this was the broad overview how we go to this intrinsic catalog. I will now skip the details about how we do the image simulation, the source extraction, and also the inference, and jump right into the results where we applied this framework to real data. And in our case, we used HSC deep fields. The HSC deep fields are a very interesting data set for this problem because it is very deep. We can actually constrain the galaxy population model to quite high redshift. And it also almost fully overlaps with the Cosmos 2020 catalog. And in the Cosmos 2020 catalog, we have high quality photometric redshift information, for example, from LeFair and EASY. So we can use these photometric redshifts to also validate the performance of our pipeline in terms of redshift estimation. The first thing that we had to do was to validate our emulator, like the emulator going from the intrinsic catalog to the measured catalog, to check that it obtains unbiased parameter constraints, which it does. And then we could explore more than 30 different model adaptations, which you basically see here on the right in this image. So we could check the robustness of the model, but we could also test what kind of model adaptations potentially improves our diagnostics. After we defined a fiducial model, we then did the final comparison. And here you see we have a very good agreement with the data in the black curves compared to the GalSBI simulations in blue. So magnitudes agree very well, the colors agree very well, and also the size distribution agrees very well. Especially the size distribution agrees better than it did in a previous work. We also compared the photometric redshift distributions. And here, again, you see we have an improved agreement compared to previous work. But still, you see that since in this version of the model, we have not included our clustered positions, you see that we don't have any cosmic variance effect, and therefore the redshift distribution is smoother than the ones by Le Fair and Easy, although the mean redshifts agree quite well. And we also tried a first very simplified version of atomic graphic bin assignment, which also shows quite promising results. So I showed you the GalSBI galaxy population model that we constrained with observational data using SBI. If you want to read more about it, I refer you to the paper that is linked here. If you would like to use the GalSBI model to generate realistic catalogs, then you can do that quite easily now with the GalSBI Python package. So it's basically 3 lines of code to obtain a realistic galaxy catalog. If you also want to use UFIG to generate realistic images, we also publicly released that, and you can use it with or without GalSBI to generate the catalog that you want to have in your image. Both of these software packages are also linked on GitLab repositories here. And I also showed you some of the work we're currently doing. So one is, of course, realistic positions that we try to assign to our galaxies using the SHAM-OT framework. Here's a very preliminary plot where you see the redshift distribution using the random positions where we don't have any cosmic variance, and therefore the distribution is very smooth. And then the positions when we use SHAM-OT, when we, as expected, have like these spikes due to the cosmic variance. And last but not least, we would also like to extend our framework to infrared data and also the spectroscopic data, such that we could validate the model across a broader wavelength range. And with this, I would like to conclude my talk, and thank you for your attention.